the root array that without having to actually find the roots will tell us exactly how many of the denominator roots of the poles have positive real part. And of course, we are stable, or zeros, we'll also point out zeros. We are stable if all of them have negative real part. Same thing applies for closed loop system, except for a big problem. That the closed loop denominators, the characteristic equation, which in the class notation is 1 plus GUTC, is not a polynomial equation because of the e to the minus ds. So we can't use the root array as it is. We can, however, do an approximation of the root array, and by the approximations approximate e to the minus ds as the ratio of equal order polynomials in S. And the first order by the is if we use the Padé approximation, then the characteristic equation becomes a polynomial equation. So we can use the root array. However, unfortunately, it adds the wrong way. Root array can say stable, while in reality it's unstable. Still, it has a huge advantage. It's the only method that doesn't require to first plug in values for the controller parameters. And what are the controller parameters? 3 parameters for classical PID. They are the controller gain, Kc, the integral time constant tau I, and the derivative time constant tau d. All other methods, you have to give specific values of Kc, tau I, and tau d, and do the test to see if you're stable or not, which doesn't give guidance, doesn't tell you how to really design it. You would have, with 3 parameters, a 3 parameter search space is pretty large. The root array has the advantage that it can give us, that it gives us inequalities without giving specific values for Kc, tau I, and tau d, which can be very easily used for searching parameter space, and in many cases will give direct guidance. So what I do, first, if I need to design a controller, I will use first the root array to check it, and then I will use a method that doesn't have the delay problem, which is the Bode stability criterion or the Nyquist stability criterion, to verify that for the values that I choose given the root array, indeed I have closed loop stability. And so let's do a second example of closed loop stability with the root array. Okay? Last Monday, I didn't have much time, so I did this transfer function, which is an open loop unstable. Okay? Clearly, we have a denominator root at plus 1/3 for GU. So the system is open loop unstable. Without feedback control, we cannot operate in that steady state. And the question is, can we stabilize it with a PI controller? First of all, we could stabilize it with a P controller, and so obviously we can stabilize it with a PI controller, since P controller is a special case of PI. The tau I goes to infinity, and PI becomes P. But let's do a little bit better example. Use a PI controller and see what guidance the root array gives us in terms of obtaining a closed loop system that is stable. So the very first thing we have to do is form the characteristic equation. So the characteristic equation, what happened, Carlos? Huh?
Fell off the bike the other day.
What?
Yeah.
It's not broken though.
No, that's not good.
Alright. So, characteristic equation. So remember, that is 1 plus GU, GC equals 0. Or the exact characteristic equation is 1 plus 7 over 3 s minus 1 equal to minus 0.02 s times kc, and let me write 1 plus 1 over tau I s as tau I s plus 1 over tau I s, which is not polynomial. So, Julia Padel becomes approximately or equal. Okay, I'll introduce this. Approximately follows. I don't know. Is there a maximum for approximately follows? Okay. Approximately follows with a pattern. One plus 7 over 3 s minus 1. 1 minus 0.02 over 2 s over 1 plus 0.02 over 2 s. I'm trying very hard to make my truths distinct from my s's.
Thank you.
Why did you change the form from 1 plus 1 over tau over s to common denominator? Do you have to do that?
Well, because I'm going to have common denominator, so it's more convenient to look at it this way. So I also have here kc, and I have tau I s plus 1. I will need to have a common denominator. Okay? So sooner or later I will have to rewrite it. Okay? So that's the approximate characteristic equation. It's a ratio. We can put common denominator. So if we have a common denominator, so the common denominator is what? Is 3s minus 1 times 1 plus 0.02 over 2. Well, let me write 0.01, okay? This also makes my 2's disappear. Times tau I s, and the numerator is the 1 for the common denominator becomes 3s minus 1, 1 plus 0.01 s tau I s, and plus the rest of it is 7 times 1. Okay. Then we have kc, and then we have tau I s plus 1. So we have a ratio equals 0. That means the numerator has to be equal to 0. Okay, we cannot take any we cannot choose a parameter to become infinite. Okay, and even if we chose tau I to become infinite, still, well, okay, then you have the pi form, the p form. So That means the numerator has to be 0. And what kind of equation is the numerator? It's a polynomial. Of what degree?
Second. Oh, third.
Third. So let's collect the powers. So s cubed, I have for s, and s cubed here. This is only quadratic. So the only s cubed comes from here. And what do I have for s cubed? I have 3 from here, 0.01 tau I. So it will be 0.03 tau I times, I don't know the times s. Well, I'll put the pencil here. Times s cubed. Hope I didn't mess up. Let's 0.03 tau. Yes. Okay, let's collect the s squared ones. And all right, from here, remember the s multiplies everything, tau is multiplies everything. So it's the first order from these two that will give us the quadratic with them. So I get from here 1 times 3 minus 0.01. So that's 2.99. And I have from here tau I. So that's the s squared contribution from this part. Think okay? Okay, let's figure out the s squared contribution from this part. I have 7 kc minus 0.01 tau I. So minus 0.07 kc tau I. I didn't mess up, that's the s squared. Okay, s terms. Let me just double check that. I didn't mess up. 7 kc minus 0.007. So minus 0.007. Yeah. All right. First order, I have s is what is zeroth order from here. So that's minus 1, the zeroth order, times tau I. So I have a minus tau I from this part. Right? And from this part, first order is 7 kc, and I have minus 0.01 plus tau I. So plus 7 kc, and I have tau I minus 0.01. Another parenthesis. Zeroth order, this doesn't have anything, this is the only one, and that's 1 times 1 times 7 kc plus 7 kc equals 0. Andrea, question? Christian, okay? Jonathan? Ashley? Okay, so let's form the Ruth array. How many rows will it have? 4 rows. Okay, let me see a hand who will help me form the first row. Andrea.
0.03 tau I.
0.003, right? 0.03 tau I. Yeah.
And whatever's in front of the s goes
So what's that? Yeah, to the right, what do I put?
Yeah, like the coefficient of S.
Okay, so minus tau I, and okay, plus 7 kc tau I. And then minus 0.07 kc. Thank you, Andrea. Someone else tell me what the second row would be.
Is it 2.99 tau I minus?
That's 2.99 tau I goes here, minus 0.07 kc tau I. Let me repeat what we are doing. First row starts with the coefficient of highest power, every other power until I run out of coefficients. Second row, the missed coefficients. Starting from second power, and what's the next one I write? 1?
7?
1. What's the next one? Not 7. but
0?
7 kc.
7 kc.
Oops.
The coefficient of the 0th power. That's the 0th power.
Yeah.
All right. Okay. Who will read?
So the third one, the third row is going to be a negative tau.
Okay, no. I'm not going to ask for the third row. I'm going to do easy things first. Who will tell me what's the fourth row? Thomas. 7 kc. Remember the structure is inverted staircase, and the corners are always the same. So without any discussion, that's immediate 7 kc. And that leaves only one element. And Rim, you're ready to volunteer this one, right? So let me take you. Okay, I'll put a minus. And determinant, what's the first column?
For number 3,
Yeah, for number 3, I'm doing this one.
it's going to be 0.03.
Tau I, right?
Yeah, 3 tau I. And 2.99.
Minus.
Minus 0.07 kc tau I.
And what's the second column?
The second column, it's negative tau I plus 7 kc.
Exactly this.
Tau I and 7 kc.
And what's the denominator?
0.03 tau I times 7 kc.
Yeah, 2.99 tau I.
What's the denominator of this?
Oh,
First element of which row?
oh, yeah, the first element, 2.99,
Exactly, of the row
yeah,
above.
above.
So let me summarize what Rim did. So it's always minus determinant of the first column of the 2 rows above. Always the first, no matter if the element is here, it will always be first column. And the second column is going to be from the 2 rows above, the column immediately to the right of that element. So if it was a third column element, I would be looking at the fourth column from the 2 rows above. Here's the first element, I'm looking at the second column.